Okay, hi and welcome to video notes on arithmetic sequence. This section of notes could be stuck in a lot of different places, but we're going to take a look at it here. Now, we've done these, you're very familiar with these. It's really nothing more than saying, hey, let's look at an XY table in a little bit different fashion. Okay, we're very familiar with these. Actually, we're very comfortable with absolute values, linears, of course, even exponential functions. But today we're really just going to kind of focus on the y's, and that's what we're going to refer to as any type of numbers that have a sequence to them, meaning that they have a pattern that are generated. We're going to call a sequence. Okay, that's where this term sequence comes from. Now, you did some pattern work on a worksheet just the other day to become familiar with just patterns in general. Again, every list of y values that we've seen so far in Algebra 1 is really just a pattern. There's been some function rule um, that makes these y values come out. We put different values of x into them, and we get out different values of y. And that's all we've been doing. But now we're just going to take that same concept and look at it a little bit more specific in terms of the y values, let's say. So any one of these y values, we're going to reference as a term. Okay, we're going to just call those terms for right now. If these sequences have some value between them that are added, or I'm sorry, some operation between them that are added and subtracted, then we're going to call them arithmetic sequences, which really just says we're adding and subtracting between our terms, which makes essentially all of these linear functions. Okay, so hopefully you're kind of getting the correlation. These are what we're going to work with today, just linear functions. We're just looking at them differently. And that's all I want you to think of with this. And again, we're comfortable with the common difference or constant rate of change, also known as slope. And that's kind of everything that you need to know for this section. I'll give you a little rule. There's two ways to write these. One we're very familiar with that might look a little different, and one that's kind of something a little bit new, but really easy to handle. So let's break into this a little bit. Let's look at some patterns here. Here's a pattern that we have here. It says describe these, or describe the pattern in the sequences. So we know two different ways to do a pattern right now, which is that common difference. And we also know common ratio. We're going to save that for the next day's notes. We're going to call that geometric sequence. That's where they're going to multiply or divide up. So today we're really just going to work with the common difference, but we're comfortable enough to be able to identify common ratio right now. So how do you identify a pattern between y values, especially if you're not given any x values to go with it? And that's really the difference between everything we've done and now. We can make some assumptions that this is the first term, and we'll talk a little bit more about that as we get there. But in this one, let's go ahead and see what's happening between my y values. To go from 3 to 6, I'm adding 3. To go from 6 to 12, I'm adding 6. To go from 12 to 24, I'm adding 12. Well, we know that addition and subtraction here, it's not that. So this is definitely not arithmetic, right? Meaning that it's going to add itself up. Really what's happening here, if we get away from addition and subtraction, we start to look at these as a division or multiplication. We know to go from 3 to 6, it's a multiplication of 2. And from 6 to 12 is also a multiplication of 2 and all the way there out. So really what's happening here is that if we're going to describe this pattern, it's a doubling. And we're just looking at patterns kind of generally right now. It says find the next three terms. So what do we got? 48, we get 96, and I think it's 192. Is that correct? I'm doing that without my calculator. All right, and you can look here. Here's another set of sequences. This one happened to add up, which means it's increasing by 4. We get 23, 27, 31. And you can take a look at that example there. All right, let's take that to another level. So let's tell if these sequences are arithmetic. If so, what's the common difference? Kind of the same thing we just did, but we're going to identify, instead of saying, what's the next three parts in the pattern, we're going to call them arithmetic. So from -5 or -11 to 5 here, our increase is by 6. And this increase here is going to be by 5, and this increase here is also by 6. So we can see here that this one is not increasing by the same amount. Actually, maybe I should pause that. All right, so let's take a look at this set of arithmetic sequence questions here. They want us just to identify if it's arithmetic, and then if it is, what's the common difference? So if we look from -11 to 5, we know that that has to be plus 11 plus 5 more, which is going to be 16. And then from 5 to 0, we're going to be decreasing by 5, so that's a -5. And then we go back up to 6, so that's a +6. We can say that this is not arithmetic, right? And there is no common difference with these because there's no constant change there. Looking at the next one, we go from 12 to 23, which is plus 11. And then we go from 23 to 34, which is also plus 11, and from 34 to 45, which is plus 11. So we can say that this is an arithmetic sequence, and the common ratio, I'm using shorthand here, we won't use that in our class, but right now I'm going to steal that just for a second. We're going to say the common ratio is 11. All right, and then there's two more examples here that you can take a peek at. All right, jumping over to the next page. Here's the rules that I was telling you about. So a recursive arithmetic sequence formula says that if any term that you want to find, you're going to take the previous term, that's what that stands for, and you're going to add the difference. It could be subtract, if it's a negative difference, but whatever it is, you need the previous term. Let's write previous term there. Okay, previous term plus the difference. Now, in an explicit arithmetic sequence formula, I'm going to get rid of that. I don't like the way that that looks there. We saw how this transformed into y equals mx plus b, which is essentially what we can do with it. But the way that this formula works, and what I want to see you do in your notes and on your homework here, is you have to have the first term, then you're going to add n minus 1, which represents the previous term, and then we're going to multiply by the difference. Okay, and that's going to get us to wherever we want to go. So if we wanted to get to that 100th term, we can plug in 100 right here, and it's going to jump all the way down. So just to recall, a is the first term, a to the sub n is the nth term, a to the n minus 1 is the term before an, or previous term, n is the number of the term that you want to get to, and d is the common difference. So what does that look like? Well, here is a table for us, and instead of trying to write it the way that we've done before, let's see if we can use it wants us to write a recursive and an explicit for it, not in slope intercept for it. So we're going to first look at this and see if we can find the common difference. Okay, our x's go in order. That's always good to note. So to go from 4 to 14, we notice that we're adding 10. From 14 to 24, we're adding 10. And 24 to 34, we're adding 10. So the next term in the sequence, or a sub 4, the fourth term, we're going to add 10 to 34, and we're going to get 44. Pretty simple. Okay, you can see that happen over here, right? So I found that our difference was 0.5 here, and you can see we'd add another 0.5 to the next term in the sequence. So if we're at the fifth term, we want to get to the sixth term, we would have added for the fourth term to the fifth term, we'd add another 0.5 or 2.5. All right, as for the recursive rule, we're going to take the previous term and add in our common ratio. So for our recursive rule, we're going to say a to the n equals a to the n minus 1 plus our common difference, which is 10. We leave this there because we don't know which term you're looking for. If you said you wanted to find the 100th term, you'd have to know the 99th plus 10. Again, that's limited. You don't want to do that. That would take a lot of calculations. The explicit rule, though, let's leave this just a little bit further down. We're going to say a to the n is equal to our first term, and in this case, this one right here is our first term, right? There's our y-intercept. So there's our first term. So our first term in this case is just the y value, or 14. Okay, we're going to add in, we're going to leave this as n minus 1. That represents what number you're going to plug into the term that you're going to find there. And then we're going to add in our difference, our multiplier difference on there, which is 10. Now we can clean that up if we'd like to and make it look like a slope-intercept form. We could go ahead and distribute this to two terms here. So we'd find out that it's 14 plus 10n minus 10, and then we could say that a to the n is equal to 14, 4, because negative 10 plus 14 is 4 plus 10n, and there would be what we would call the slope. Here would be what you call the y-intercept. So, but we can leave it like this here if it's asking for an explicit rule. Okay, here's another example. You can see two more examples. Make sure you check those out. Write those down in your notes. All right, let's move down. Try some more examples with this so we can become comfortable with it. It says write the first 6 terms of the arithmetic sequence, which begins at 5 and has a common difference of a half. So I wrote down, because this is only a few moves, right? We only have to go 6 terms. So in this case, the recursive would benefit us the most. You're like, Mr. Hallam, aren't you just taking 5 and adding a half to it 6 times? Absolutely. But let's practice our rules here and see how it looks. So if we're going to use the arithmetic sequence, I'm going to blow this up a little bit, maybe. There we go. So let's use this arithmetic sequence here. We know our first term is 5. We know our common difference is 1/2. So it would say take the previous term and add 10. So if we want to go to the second term of the sequence, because we know the first one is 5, we're going to say 5 goes here, and then we're going to add 1/2. It's going to give us 5 1/2. So if we started our sequence would start with 5, and we just calculated the second term in here would be 5 1/2. And we're going to calculate the third term in our sequence here, which would be taking 5 1/2, because that's what A2 is equal to. The previous term is 5 1/2, and we're going to add another half, and that's going to get us to 6. So the next term in our sequence is 6. And you're like, can't we just add a half? Yeah, but we're just practicing right now. So let's finish the last one. So we're going to take 6, because that's the previous term. That's what A3 is equal to, previous term, and we're going to add a half, and that's going to get us to 6 1/2. And I think we need one more term. 1, 2, 3, 4, and we're going to go to 7 and 7 1/2. We'll do it on the sequence. So that shows you how the recursive formula works. Really easy. You might be able to do it in your head, but we can write it out and show our work, which is always nice. All right, this one says we're going to go down to the 20th term of an arithmetic sequence, but they gave us A3 this time, or the third term of the sequence, and they give us a difference of -2. So for this one with 20 terms, I would not most likely do a recursive formula, because that means I've got 19 calculations. So I'm probably going to try to write the explicit rule, and that just means after I write it, I've only got one calculation. So that's the route that we're going to take. So taking that road, I'm going to write down the rule for explicit, the general rule, which means any term that we're looking for, we're going to take the first term, add it to n-1 times d. So let's go ahead and start to do that. But you'll notice we don't have a sub 1, or the first term. We've got the 13th term. So just like before, where we kind of see the difference of moving between these values by half, and we could do it in our head, we're going to kind of do that over here for the third. Well, if the third term of the sequence is 13, and we know our sequence is decreasing by -2, so if we wanted to say a to the sub 4, the fourth term, we'd subtract 2 off, it would be 11. So this is just kind of a vertical representation of that. To go backwards, we're not subtracting 2, we'd have to add those 2 back on. So to get to the a to the second term, or a sub 2, the second term, we'd add 2. And to get to the first term, we'd add another 2, which would give me 17. So using the pattern and using the sequence, we're able to get back to the first term, which is 17. So I'm going to write 17 there. I'm going to go ahead and put plus n-1, because that's the number we're going to put into 20 here in 1 second, but we're going to put in the d value, which we know is -2. All right, so now that we've got that as set up, we're going to go ahead and plug in 20, because that's our recursive rule. So that's, oops, that's too big. We've got 17 plus 20 minus 1, because now we're finding the 20th term, and multiply it by -2. Let's jump up here and finish our calculations. We've got 17, and we got 20 minus 1, which is 19. And we got that, multiplied that by -2. Okay, so we've got 17 plus 19, plus 19 times -2, which is their difference. Let's go ahead and multiply those out. We get 17 plus 30, -38, right? Because there's a negative there. Let's not lose that. Minus 38. And we find out that the next term is 21 for the 20th term of the sequence. I'm sorry, -21. Okay, so let's take a look at this last problem here. It says a school has, I changed some of the wording here. So a school has 75 calculators this year and purchases 25 calculators every year after that. How many calculators will there be after 10 years? It says write a recursive formula that represents the situation. Then it says write an explicit formula. Okay, so we're going to go ahead and start with the recursive. Those are usually pretty quick and easy, right? So what we're looking at in general form is whatever term we're looking for, we have to have the previous term plus the difference. So in this case, our difference is 25 calculators per year. So we're just going to add 25. So there's our recursive formula. Now let's get back to the explicit one. For the explicit one, here's the general form of it. A sub 1 or a sub n, whatever term you're looking for, you need the initial term and the difference. So in this case, we don't have the initial term. What we start with is 75 calculators, because that's how many they began with, your y-intercept, your initial amount. So to find our first term, let's go ahead and use the recursive formula here, which is the previous term we need for a sub 1, or if we want the first term, we have to look back at the 0 term, so 75, plus whatever our difference is, which is 25, and that gives us 100. So we use the recursive formula to find our first term of 100. So let's plug that in. So say a sub n equals 100 plus n minus 1, and our difference is 25. So let's go ahead and clean that up. Actually, we don't even need to clean it up. We're just going to use it as is. So we're going to say a to the 10th because they want to know how many calculators there are in 10 years. So we're going to say a to the 10th, which is 100, plus 10 minus 1 is 9 times 25. If you do that calculation, you're going to find out that it's 325 calculators after 10 years, starting with 75. All right, so just to kind of review, there are two main types of arithmetic sequence formulas. Recursive, which is really only useful for moving, knowing the previous term and the next one. So this doesn't go very far, right? It's limited in its use. And then the explicit, which is really nice because you can jump around to the sequence anywhere you want. And you can kind of think of it as a slope-intercept form, if you will. We can change it into that if we wanted to. All right, so there's your notes for today. We'll see you in class, and good luck with your homework.